Okay, welcome to lecture 9. So in this lecture, I'll first continue what I did yesterday, or I'll develop a little bit more on the theme of yesterday, and then I'll talk about non-Abelian or Yang-Mills gauge symmetry. So before I do that, are there any questions from yesterday? Okay, I hope the notes are regularly available and the videos, and also whenever people point out corrections to me, I have made them in the notes. So even if you look at the old notes now, all the mistakes should be corrected. If you have any corrections to suggest, please email them to me, and it's much easier than if you show me after class. And also, please do it as soon as you find out. Don't wait 1 month to let me know that I had some wrong statement a month ago. So, okay. With that, let me recall that yesterday we discussed gauge symmetry, and yesterday we had coupled some scalars and fermions in the problem, but today we'll forget about scalars and fermions again. We had simply discussed this Lagrangian, and we gave some argument that if you fix Lorentz gauge, then you can explicitly see that A mu is reduced to two transverse components relative to the direction that the wave is moving in. And that gives you a sort of convincing understanding that even though it's a 4-component vector A mu that this depends on, so F mu nu is curl of a 4-component vector, that would lead you to think that there are 4 fields associated to the electromagnetic field. There should be, after quantization, there should be 4 particles, but that's not true. And you can see it's not true by fixing a gauge, and you always find that 2 out of these 4 get removed and 2 remain. And I emphasized in a previous lecture that although this is a complicated situation which is not found in other areas of physics, namely you have lots of degrees of freedom, you have extra degrees of freedom, and somehow they go away. It's a good situation because only a 4 vector can transform in a sensible way under Lorentz transformations. A 2-component vector cannot. Okay, so if nature wants a 4 vector under Lorentz transformations, but also a wave which has only 2 transverse polarizations, then nature has no choice but to put that 4 vector in a gauge theory with a gauge invariance. This is the point which I tried to also emphasize yesterday. Now, to go on from this, let's try something which looks on the face of it quite silly. Let's add by hand a mass term for this vector field. So here's a massive vector field. Okay, why did I put a plus? I'm anticipating, so as you know, with the plus, the terms with mu equals I come with a minus sign, and mu equals 0 term comes with a plus sign. So, but the ones with mu equals I, those could be some of the transverse polarizations, and they should come with a minus sign because for normal fields, the mass term for bosonic fields, the mass term must have a minus sign. We already saw that in the Klein-Gordon case. So the sign is wrong, so to say, for A0 and correct for the other 3. That's why I chose this. Okay, now with this, let's just try to understand this system. Of course, it doesn't have gauge invariance anymore because when I shift A by del mu lambda, this term doesn't remain invariant. So this has broken the gauge invariance. You have seen something roughly analogous in the case of scalars where there was an axionic shift symmetry and mass term broke that symmetry. So here there's something else and the mass term breaks it. This time it's a gauge invariance. Okay. What's the equation of motion? So earlier it was del mu F mu nu equals 0, but now it's del mu F mu nu equals m squared A nu. It's a quadratic Lagrangian, so it's not hard to vary that extra term, and obviously you get this on the right hand side. So this is the equation. Okay. Now something very interesting happens. Supposing, so this is a set of 4 equations. Supposing I take the divergence with respect to the new index on both sides. Okay, so the equation of motion implies that this is equal to m squared del nu A nu. Okay, so far clear? Now what is this? 0. Because del mu is symmetric in the indices and this is anti-symmetric, so this is 0. So that implies that del nu is 0. Now see something interesting. Yesterday we chose del nu to be 0 as a choice of gauge and we called it Lorentz gauge. Today we didn't choose any gauge because we can't choose a gauge because there is no gauge invariance. But the equation of motion has put the same condition on the field. Okay, and that's very nice because it's one condition on the field. This gets rid of, if we do things properly, we already know this would get rid of one polarization at least. But in this, the particle associated to this doesn't satisfy k squared equals 0. It satisfies k squared equals m squared. Okay, so that other condition which we saw yesterday, that redundancy, which removed the transverse degree, the longitudinal degree of freedom, that won't be there. Okay, but so we have only one condition and not two. Okay, we have one condition on A mu, which is the for divergence-less condition. Also, by the way, this is not our choice. Yesterday it was our choice. This was a possible condition because you could have other conditions like Coulomb gauge, but today it's not our choice. It just follows from the equations which follow from the Lagrangian. So we have no choice. Okay, and we have no second condition due to redundancy. So this is actually pretty good. It looks like we got part of what we want in life without having gauge invariance. Without gauge invariance, we got a condition on this 4-component field, and hopefully that condition could be used to remove the time component, which is the one that we really wholeheartedly dislike, and leave 3 components, A1, A2, A3, and that means that if there's an associated wave for this, it would have 2 transverse and 1 longitudinal polarization, and there's nothing wrong with that. There are such waves in nature. Sound waves are like that. In fact, the wave, quantum mechanical wave associated to any massive particle, which is described by a vector, by this procedure, gives me exactly 3 polarizations, and it's not wrong. So we are actually in a fairly good shape. Okay. Now what happens if we insert this constraint back into the into the equation of motion? You remember that this equation has 2 terms, del mu A nu, and minus the other way around. But that second term precisely goes away because of the constraint, and so the EOM, equation of motion, becomes box A mu equals m squared A mu. So again, as we did yesterday, the equation of motion is that of 4 Klein-Gordon fields. I mean, it's the same equation as if it was for 4 Klein-Gordon fields, all the components of A, and there's one supplementary condition, del mu A mu equals 0. Good. Now we can actually do the same steps as yesterday to find out the physical states. And yesterday, if you remember, what we did was to go to momentum space and also choose a standard reference direction for the for momentum. So it was 1, 0, 0, 1. Okay, but that was anticipating a massless particle, and now we won't be able to do that because it's not a massless particle anymore. So we'll have to choose a different reference momentum. So the first thing is that if we go to momentum space, in momentum space, we will find this relation. It's actually the same as this relation. You just take this and go to momentum space. I think I got a sign wrong. This is the correct equation. Why didn't any of you correct me? I had a sign wrong. Most classes I've taught, both in TIFR and ISER, I've been corrected as soon as I make any mistake, and little disappointed, and I hope you'll be better at finding my mistakes, because it's part of your participation in the lecture. Lecture is not just something which I deliver. Okay, fine. So now again, so we have this. We have the oscillators A mu and A mu dagger. and we have the four states obtained from the vacuum by acting with AU dagger. And now the transversality condition says K mu times this is 0. Because K mu is 0 when it multiplies the Fourier transform of A, and that's precisely what these A and A dagger, small a and A dagger are. And so K mu, so polarization parallel to the form momentum when dotted with this must give me 0. This is the same condition as del nu A nu equals 0. Just transport it to Fourier space, momentum space. Okay, now let's solve this condition by finding a reference basis, a standard form for K. So if K is supposed to satisfy this, what's the easiest 4 vector we can think of?
M and minus M in the first and last.
M and minus M.
M000.
M000. Minus M will spoil everything. It will be massless, M00. And what frame is that? The rest frame. We just go to the rest frame, which we couldn't do yesterday because a massless particle doesn't have a rest frame. Okay, now we are in the rest frame. So very good. So what does this tell us? That A0 dagger on 0 is 0, and we are happy. It's exactly what we were hoping for. The time-like polarization is gone as a consequence of the gauge of this, not gauge, of this condition, which in turn follows from the equation of motion. Okay, good. And after this, there's not much to say. Whatever I have to say more is written in the notes, and I'll leave it to you to read. It's pretty standard after this, but there are no more conditions. That's the point. So A1, AI dagger on 0 give me 3 physical states. And so in the massless case, there are 2 physical states, and in the massive case, there are 3 physical states. Okay. Now, why is all this important? Well, apart from the photon, there are no known vector fields in nature, fundamental vector fields in nature, which are massless. The photon is, as far as we know, exactly massless, and all the gauge stuff I discussed applies to the photon. But none of it can apply to other vector particles which have a mass. We must have the mass term if they have a mass. And then today's discussion applies rather than yesterday's. And there are several such particles known experimentally, such as the Z, W plus and W minus. Also mesons like the rho meson, which is not fundamental, so it's not elementary. It's made of, like all mesons, it's made of quarks and antiquarks. But still you might want an effective description of it. And for that, you would need a vector field, but you would need one with a mass and not a massless one. So this is very good. However, all this has been done at the level of the free theory, non-interacting theory. I have only discussed the free massive theory. Okay. Now, in the case of the free massless theory discussed yesterday and previously, when we add interactions, which we also did yesterday, we preserve gauge invariance. When we preserve gauge invariance, then all the good features which were there in the free theory will survive in the interacting theory because they are due to gauge invariance. Okay, but it's pretty easy to see that if I add interactions to this theory, I won't preserve this nice feature of having del mu a mu equals 0. Can you see it? You can. Some people are nodding. With interactions, our equation is going to change to del mu f mu nu equals m squared a nu plus some source term j nu, like the term which appears in Maxwell's equations. But it will typically come from some other fields, for scalars or fermions. Okay. Now if I take the divergence, then I get del nu a nu times m squared is del nu j nu. Now it's good if the current happens to be conserved, but it's not guaranteed that such a thing will happen in the massive theory. In the massless theory, we always get conserved currents as the source. In the massive theory, we may or may not. And so it's not so clear whether interactions will preserve this nice feature that A0 dagger on 0 is 0. In fact, with interactions, we can't really discuss this because this is a purely free theory statement. These oscillators come when we expand the free solutions of the equation, solutions of the free equations. Yeah, there's a question?
So then the minus.
Minus sign. Sure. Thank you. Good. Okay. So interactions could be more tricky. I'll just leave it at that. And we'll look into that when we come to an actual discussion of a second round of discussion on massive vector fields, and that time we would have first learned how to quantize field theory through path integrals, and then we'll revisit this question.
Sir, will there be minus sign in the first equation of also that you wrote?
This one?
Yeah,
There might be.
because that is not giving this one.
Good. Yeah, maybe. What do you think?
It's not giving this equation.
It's not giving this?
If it's correct, that is not correct.
I think it is giving this. Ah, it's not giving this. Yes. Very good. Thank you. Absolutely. Yes.
So, A not dagger acting on 0, giving 0, it's like something we haven't, this kind of ladder operator, we haven't seen before. So, is this something?
We saw it yesterday also. We saw A naught dagger on 0 is same as A3 dagger on 0.
Mhm.
That means A naught minus A3 dagger on 0 is 0. So it's very important to understand what this equal sign means. Okay, when we quantize these ladder operators, we get a bunch of states. We don't know whether they are 0 or not 0. We just assume that they are normal states with some kind of normalization. But then if we try to find the norm of this state, we find it's negative. Then we discover that at the classical level, the theory has a constraint. So the idea of quantizing all 4 components of A mu was wrong in the first place. If it's constrained, we are not allowed to independently quantize all the components. Supposing one component was 0, like in Coulomb gauge A0 is 0, then we're not allowed to make a mode expansion of A0 in terms of oscillators. We just forget about it right there and then. Here, because it's a constraint which is not solvable in a local way, so we cannot invert this constraint and find A naught in terms of the other 3 A's, at least not in this space. And even in momentum space, we would have a problem if K0 is 0. So it's a bit tricky. So we prefer to keep the constraint because keeping it is Lorentz invariant. While solving it, we would again break Lorentz invariance. So we pretend that we are going to make a mode expansion on of all the 4 components, but after making it, we impose these as conditions, auxiliary conditions. And if they set something to 0, it just means this is declared to be 0. That's all. It's a statement about the Hilbert space of the theory. So that's how it works. It does look odd. It's not equal to 0 in a calculational sense. There's no calculation which will make this equal to 0. You just have to say it's 0 as a consequence of this and the choice of momentum frame M000. Of course, any other momentum frame will do because K has to be time-like, and therefore a time-like component, maybe not A0 exactly, but some time-like combination of the A's will be set to 0. Which one is set to 0 doesn't matter because the 3 orthogonal ones will be space-like and those are the ones we keep. Okay, good. Okay, so for the moment this is end of that discussion and we'll revisit later.
So in the left,
Yes.
in the right hand, there will be minus and minus and
Where?
because in the
Ah, yeah, here. So the previous comment cancelled out. Very good. Yeah, thank you. Good. Okay, any more questions on this point?
Sir,
Yeah.
when you are acting A0 dagger or A1 dagger, so is it forming a particle of momentum P1 or P0? Then you are adding it is a linear combination. Like they are superposing or they are 2 different particles? And
No, I can it's superposing in the sense that I can superpose polarizations, right? If I have an oscillation in the x and the y direction.
how do we know that those are polarizations?
Well, it's obvious because those are the directions when in the wave equation, those are the directions in the wave, right? So they are polarizations. If it's not clear, we can talk about it later. Now, and hopefully this will be the last lecture on classical field theory in this course, though we may revisit some of the issues later. And in this lecture, I will introduce Yang-Mills theory. Okay. Now, the idea of Yang and Mills was kind of nice, and it was mathematically inspired. And the idea was, we have non-Abelian global symmetries. For example, for a complex scalar or a complex fermion, I can multiply by a unitary matrix, and this can be a symmetry. And unitary matrices form a non-Abelian group, because if I have one unitary matrix U1 and another one U2, and I multiply them like this, then this is not equal to U2 ij U1 jk. The order of multiplication is important. It's true of generic matrices. In fact, the only matrices which don't which actually satisfy the equality are, this only happens if one of the matrices is identity or proportional to identity. Then the order doesn't matter. Otherwise, the order generally matters. Okay, there are some more cases. For example, if U2 was U1 inverse, then also the order doesn't matter. So there can be matrices which commute. Okay, but pick any two arbitrary matrices and they certainly won't commute. Good. So this is non-Abelian. But this Uij is constant, and we discussed this quite thoroughly in the first part of this course. The first 2-3 lectures of this course, we showed models which have this symmetry, which have similar symmetry where U is replaced by O. So these are the complex and real vector models. Then we showed models where phi is a matrix and this symmetry acts from both sides. And then we showed models where G is a group valued matrix and two independent unitary symmetries act one from each side, all those kind of models. In all of those cases, unitary or orthogonal groups show up and they are always non-Abelian. Okay, the second observation is, we also have gauge invariance. I keep saying gauge symmetry, but I hate that expression, so I have to correct myself. But this involves abelian only, because, well, we discussed quite general abelian gauge symmetries yesterday, where a field like phi of psi picks up a phase and A shifts by gradient of that phase. But that phase is just one function, and so if I do it twice in two different orders, it doesn't matter. So A goes, I've done this before, I think. A goes to A mu plus del mu of lambda 1, then I add del mu of lambda 2. Well, the answer is del mu of lambda 1 plus lambda 2, and it doesn't matter which one I do first. So, combining these two observations, the question is, why not non-Abelian gauge invariance? And you should certainly read the history of this paper. I'm sure there are articles, and actually I'll try to find some nice ones and link it for you from the blog page. It's a very strange way to do physics. Unless there's a physics problem which is supposed to be solved by this, why should our minds go in this direction? Okay, all very well for mathematicians, because mathematicians often take two structures and try to generalize them into one or combine them, or that's how mathematics develops. But it's very odd for physicists, but it's what they did. And in fact, they tried to impose it on some isospin symmetry, which is a global symmetry between protons and neutrons. And then they thought maybe it's a local symmetry. Actually, today we know that it's a very accidental symmetry coming from approximately equal masses for the up and down quarks, which didn't have to be equal. Nature has just chosen them roughly equal. and it's not a symmetry that governs something very deep about the standard model, and so making it non-abelian is somewhat pointless. So motivation was sort of wrong, but the idea was great. So let's pursue the idea, and then later in this course, but also in Arun's course for those who are taking it, Advanced Particle Physics, it's basically the entire course in some sense, because standard model is the underlying thing. It rests entirely on the foundation of these theories which were inspired by this question. So right now, without asking what's the physics, we'll try to pursue the question. And it's beautiful that Yang and Mills actually, although they wrote a few pages of paper, the paper was already done in the first 2 or 3 equations. Okay, it was just one stroke of inspiration, and it's an inspiration that any of us could have based on everything we have read about. So let me try to repackage their inspiration. Let's imagine a field strength, so a vector potential that instead of being just a function a mu of x, let's imagine it's a matrix. So I put this thing under it for matrix. In the notes, it's boldface for matrix. Okay, and just to be definite, let it be a Hermitian matrix. And as we already saw once, if we make a matrix Hermitian as well as traceless, then it's in the algebra of SUN. The trace part is another U1 which combines with SUN to make full UN. So UN is a group that breaks naturally into U1 and SUN. Yeah, question? Okay. Okay, so let's imagine that, and correspondingly a field strength F mu nu, which is also a matrix of the same kind. Okay. Now, we need to be careful. You might say, well, since we are imagining things, let's also imagine that this is curl of that, del mu a nu minus del nu a nu. Okay? We shouldn't imagine too many things. We are only imagining that there are certain fields, and then we are trying to, by logical reasoning, find their properties. So we are not guessing any properties for them, but the basic hope is that F should have an invariant Lagrangian, very much like what I showed you for scalar fields, which is the trace of the square of the matrix with a minus half. Well, this doesn't matter. So this should be invariant. Okay, and what should it be invariant under? It should be invariant under a transformation which sends this matrix F, sorry, it's the wrong place I'm putting it, to a unitary matrix function of X, F, and unitary matrix dagger function of X. Okay, as you can see, I've copied for F what we already know to be true for example, del mu of phi, where phi is a matrix valued Klein-Gordon field. Okay, the difference there is that F is derived from a vector, and there del mu of phi is derived from a scalar. So they are different in detail, 1 minute. But the restrictions I'm imposing are that there should be some Lagrangian which looks like the electromagnetism Lagrangian, so quadratic in F. And when F transforms under a local symmetry like this by unitary transformation on both sides, where X is, U is an arbitrary function of X, then of course trace of F squared will be invariant. So all we want is F should transform like this. Yeah, what's the question?
So what are the matrix element for A and N?
Yeah, good. Thank you. So this, I was going to do it later, but we can do it right away. Given any element of the Lie algebra of any Lie algebra, I can always decompose it over the generators, where A is summed over, and A goes over the dimension. So A is 1 up to dimension of SUN. You already know how to do this for SU2, where A goes from 1 to 3 and TA are sigma A by 2, half the Pauli matrices. Those are the correctly normalized generators of SU2. So in this way, we see A mu to be a 3-component object where A runs over 3 values. Okay, but before we get confused that this 3 values has to do with SO3 or SU3 or something, we realize that actually it's better thought of as a matrix A mu, which is 2 by 2, because the Pauli matrices in that case are 2 by 2, and then it transforms by a unitary matrix on both sides, U and U dagger. That also induces a transformation on A mu A, which we'll be writing down later on, which can be derived from this. But it's much easier to work with matrices, which is something that Yang and Mills also realized. So everything that I do can be transcribed into components. So these are called components. We did it already for scalars, and F will be the same exactly. F, the matrix, will be F mu nu A, T A. And one second, and the T's will satisfy the commutation relation. That, yes.
So sir, here we are basically demanding vectors which are matrices or
Yes,
matrices
vectors which are matrices, yes.
The components, the decomposition
Yes,
into component
good.
looks as if
So A mu Ij. This and this are the same. Here I hide the indices and put this sign under it. Here I am writing the matrix elements. So every element of this matrix is a 4 vector. That's right. Whatever kind of, you see, this 4 vector has to do with Lorentz transformations. These matrices have to do with some internal symmetries which don't care anything about Lorentz transformations. So they are just different spaces. Okay? But up to now, we have only said what we want. We haven't actually said how to do it. Okay? If we could find an F which transforms this way, then we would be happy, because we would have an invariant Lagrangian which would be gauge invariant, that is invariant under local gauge transformations. Moreover, let's imagine the limit of all this when n is just, instead of un, we have u1, the simplest case, just one field. Then we would have something like a phase here and opposite phase here, but those would cancel because F would be a 1 by 1 matrix, and that's the statement that Maxwell field strength is gauge invariant by itself. Here it would not be gauge invariant, it would be gauge covariant, and only its trace of the square would be gauge invariant. But that's all we want, because that's the Lagrangian that we would like to use. Okay? The question is, what is F? In terms of A. And also, how does A transform? So how does A transform in order that F should transform like this? It should be implied. Then I have to only once and for all tell you the transformation of A. Then this will follow, then invariance of this will follow. Yes?
So you mean the internal space of A, right? The internal space of A, right?
What do you mean by internal space
so,
of?
So this A mu, that the mu indices is only
The
one
mu
point-
indices do nothing in this
Right.
transformation. Well, they don't exactly do nothing. Remember yesterday, A mu went to del mu of lambda. Okay, so it's only possible because A is a vector. So the kind of transformation we'll find will be one which is suited for a vector. It won't be a transformation suited for something else like a scalar or a spinor. But nothing will actually happen to the Lorentz index. We won't transform it, but we will use the fact that it's a Lorentz vector index, as we did also in the Abelian case. Okay, so these are the two questions. And Yang and Mills said, very good. Let's assume, before we solve this problem, let's assume that we have also a fermion field. Again, it's very insightful, because we want to solve a problem within gauge theory. We don't need more fields, matter fields, but they brought it in, and the reason is the following. So I'm not going to use their fermion field, I'm going to use a scalar field instead. It works the same way. So let's assume we have a scalar field, and the scalar field under this same transformation transforms as uij of x phi j. Remember, early in the course we learned that there are two essentially different ways something can transform under U. If it's a vector with respect to the group or the algebra, then it transforms with a U on the left. It carries one index and it transforms with one factor of U. But if it's a matrix, it carries two indices and it transforms with two factors of U, U and U dagger. Okay, and the representation of the Lie algebra for this kind of behavior is called adjoint representation, and for this behavior it's called fundamental representation. So what they did, let's bring somebody in the fundamental representation into the problem and then try to set up a consistency condition. Okay, now they said, very good, we assume that we have such a field. Now we want to generalize del mu of phi, which arises as in the kinetic term of this, by inventing a covariant derivative, as we did yesterday in the abelian case, and we'll require the covariant derivative to have a certain property. So we'll write the covariant derivative d mu phi I, and in detail it will be del mu phi I plus an extra term, and the extra term this time is going to be minus Ig a mu Ij phi j. You can see that this is a fairly straightforward generalization of yesterday's covariant derivative, except for this factor g which has appeared here, but it's not, I'll explain that you can have it or not have it. It's a choice of convention, you could also drop it, but we'll keep it for now. But for the rest, it's just del goes to del minus Ia. The difference is del is just one differentiation, but A is a full matrix. So del just differentiates phi, but A actually acts on this vector phi by a matrix. Okay, so it's a matrix action. Okay, and this can also be summarized by saying this is del mu delta Ij, Kronecker delta, minus Ig a mu Ij on phi. I hope you can see that these two lines are exactly the same. And now they said, good. Supposing phi goes to u of x on phi, then d mu of phi will go to d mu of u of x on phi. So I can put it. Right? We don't know yet what is the behavior of A. We are just going to choose it so that this happens, and this should be equal to u on d mu phi. In other words, I'll write it out in components in a second. In other words, if I make a gauge transformation on phi, the matter field, and then take its covariant derivative, it should be the same as if I take the covariant derivative and make a gauge transformation on it. And here you can see that they have deeply understood the principle of gauge invariance as I discussed yesterday. Covariant derivative's job is to map something with good transformations under some symmetry to something else with equally good transformations. And they are saying that if phi has the good transformation, phi goes to u phi, then d mu phi should also have the good transformation that it goes to u times d mu phi. So these two operations should commute. And now let's write, this looks a bit abstract, but let's write it in more precisely and you'll see what content it has. On the left side, I have d mu times the identity minus Ig, the gauge transformed matrix A mu prime, then multiplied by the matrix U. U is always going to be x dependent. I won't always write the argument. Then dotted on phi. Matrix dotted on phi means Uij phi j. So we want this to be U on del mu 1 minus Ig A mu phi. Dotted on phi. Everything is in the sense of matrix multiplication. This matrix multiplies the vector phi to give me a vector. This matrix multiplies this. But of course here I have the original A, here I have the gauge transformed A. Okay, because here it's acting on phi, here it's acting on the gauge transform of phi. So it's the gauge transform of A. And this equation can be solved for A prime in terms of U and A. That's the idea. And in one line they wrote the solution. Is this equation clear? Let me write the solution. One of the important things, okay, first thing in the solution, I can drop phi now. I just brought in phi just to impose this condition. But if a matrix acting on an arbitrary vector is equal to another matrix acting on the arbitrary vector, then I can cancel the vector out. The two matrices must be the same. And if I do that, I find the solution, and it's worked out there, that A prime of mu is U A mu U inverse minus I upon G del mu U U inverse. So what they did was, by assuming that covariant derivative exists and has the desired property, they found that under a gauge transformation, A prime must be this transform of A. You can also call U inverse as U dagger, it's the same. U is unitary, plus that term. Now let's see whether any of this makes some sense to us from the abelian point of view. Can you see what this equation reduces to in the abelian case? In the abelian case, U is a phase and A is a single function. In this term, the phase cancels out, so you just get A. In this term, U is a phase. When I differentiate the phase, I get I del mu theta, where theta is the argument of the phase. U is e to the I theta. So I get I del mu theta. I cancels with minus I. Okay, and then the rest of the phase cancels with that. And so I get A mu prime is A mu plus del mu theta, which is the old gauge invariance, the abelian one. So this generalizes that by making this more complicated, but also introducing this conjugation by a matrix U in the first one. Okay. And now it's a bit of algebra, and I've done it in the notes, and I'd encourage you to do it. It's very beautiful because it's only manipulation of matrices, and it's easier to do without writing all the indices. You know that every unitary matrix has an inverse. U dagger is its inverse. Because of that, you can actually easily go from this to this. And now we have to find out F. So we've solved part of the problem. How does A transform? We solved that without even constructing F. Now we need to construct F. Well, again, we can use some. Okay, one more thing to note, by the way. This G is a little awkward, but what you could do is you could redefine A as A by G, so that all the terms get 1 by G, and then you can cancel G out of this equation. Okay? And if you do that, G also drops out of this equation. What will happen is it will come back into the Lagrangian. I'll describe that process many times in this course, so you can also try it yourself. Yeah, so G will in fact be a coupling constant, and we'll see that in a minute. So what is F? So the first guess we could start with is that it better have this in it, plus possibly more terms. Why? Because F should be a first derivative on A, because we want the same structure as the abelian theory, that it's a two-derivative Lagrangian. Only two-derivative Lagrangians lead to normal wave equations. So F should be derivative of something, that thing should be A, F should be antisymmetric, so this should be an antisymmetric combination. Turns out there's a new antisymmetric combination which wasn't possible before, which will come. But how do we see that? Well, we plug in this formula here, and so we calculate F prime mu nu, and we compare with F mu nu. What we are hoping for is that F prime mu nu relative to F will have a U and a U dagger on both sides, because that's what we started as our requirement. Okay, but we could get a mess of extra terms, and actually we do. So when you actually work this out, you find the following. First we'll see what happens to this if it changes in the desired way, and then we'll see whether its failure to transform the right way suggests to us what we might want to add over there to correct it. It's a trial and error procedure to fix the form of f. So we find with an easy calculation that d mu a mu prime minus del mu a mu prime with this transformation below is u del mu a mu minus del mu a mu u dagger, which is good, plus I by g del mu u u dagger minus del mu u dagger plus few more terms that I am not writing down just now. If there were no such terms, then we would have got the answer and we would have said f is this, because it's transforming in the way that we want. But here are some extra terms, and you can see clearly these are due to the gauge nature of the problem, because all of them involve derivatives on u. Okay, there are more terms. These more terms involve a's as well as u's, derivatives of u's. This term involves a but no derivative of u. This term involves no a's at all. This is called the inhomogeneous term. And when you work in a subject like field theory, you should learn to focus on one term in a calculation for some time and then bring back the other terms and combine them and so on. That's the strategy we are going to take. Our strategy is this is good, this is horrible, it wasn't there before, it shouldn't be there, and any other terms which are there also shouldn't be there. Okay, is that a fair strategy? Now we'll only focus on this term. If we can make this term go away, then we'll see what happens to the other terms. By the way, for me, this exemplifies something that Fermi always used to say, which is that when you have a problem, try to break it into small pieces. And here, this is one of the small pieces, and it's a very identifiable one. It's the piece without any a. So it should cancel all by itself. We don't care what are these other terms. They can't help, this can't help. Only this term must cancel. So what is it? And can we get some inspiration about how to cancel it? Okay, well, the inspiration, okay, I rubbed out a very important equation, so I better write it here. A prime u is u, a mu u dagger minus I upon g del mu u dagger. Okay, good. So this term I can rewrite in the following way. We've already done, I don't know if you realize, but U being an element of the unitary group is very similar to G, which was the field of the principal chiral model. We studied the principal chiral model, G was a field, and that field had an inverse G inverse, which is the same as G dagger. It was a function of X, this is also a function of X. This connection is not at all accidental, by the way. But the important difference is that there G was related to a fundamental field of a field theory, while this is related to a gauge parameter of this new theory we are trying to build. Okay, there's a difference of interpretation. But the manipulations are exactly the same, and it turns out that this term is exactly equal to minus I by G, the commutator del mu u u inverse with del mu u u inverse. How will you show that? You'll in the middle here you will insert u inverse u. Then del mu u u inverse has come. The other u is multiplying del mu u inverse. But in that there's an exercise you must have done in which you can transfer the del onto the first piece, and then you get del mu u u inverse. And that transferring of the derivative gives the minus sign. And the other term is the same as the first term with mu and nu interchanged. So here, since they have both the same object, so it becomes a commutator. Okay. And now can you see something interesting about this commutator with respect to the transformation of the gauge field? Comparing this line and the top line, can you see some object which appears in the same way in both?
The Second term.
that term just twice. Okay, so this is a motivation to correct f mu nu by adding or subtracting. I have to determine the sign. Turns out to be minus ig a mu a nu. So it turns out if I do this and now I transform these a's and keep only this term, the inhomogeneous term, I precisely get the opposite of this. So it will cancel this. Okay, so I made a big step towards achieving gauge invariance, the proper transformation of f into f prime. But I bought myself a lot of trouble because there were some plus dot 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 terms which I didn't consider. And also these a's which I have now introduced in the commutator, when they vary according to this term and not that term, I'll get something new. There will be cross terms, there will be lots of terms. But the beauty is that I have to have this term in order to cancel this term. There's no other possible way. So either this is right or Yang-Mills theory doesn't exist. Okay? If it doesn't exist, Yang and Mills wouldn't have written any paper and that would be the end of that. They were really trying to achieve something that nobody knew if it exists at all. And we are trying to replicate that calculation. And now we realize that when we add this term, we cancel this, and now it's a matter of checking that all the other terms cancel. Now we have actually a proposal for f. And you may say, well, what if I added some more terms? Problem is, there really aren't any more terms to add. Can be seen from many perspectives. One of them is that if you look at the dimensions of fields in 4 dimensions, this is a dimension 1 field. Derivatives are dimension 1, so this is dimension 2, that's also dimension 2. So G is dimensionless. This argument, I think you must have seen these arguments in QFT1. So if you add cubic and higher order, you could think of adding them, but it would complicate everything. Plus I want only 2 derivatives. So I want 1 derivative in f, so I don't want any more derivatives in the higher terms. But then how am I going to make something which has only 2 indices? If I have 3 a's, one of the indices has to go somewhere. If I take its divergence, that doesn't seem very natural. There are terms, I'm not saying there aren't any, but it seems natural that they should terminate exactly in this form. And this coefficient got exactly fixed by requiring cancellation of this term. All this calculation, by the way, is not in Yang and Mills paper. They simply said, as soon as we assume that f transforms the right way, we find that f must be like this. This calculation was in their notebooks. They didn't put it in the paper at all. But it's an easy calculation for anyone to do. And if you have any plans at all of studying gauge theory in the rest of your life, the first thing you should do is go home and work out that this, under A goes to A prime like that, f goes to f prime equals mu f, where u depends on x. So this is a big achievement. We, by combination of some guesses, some intuition, some logical arguments, we managed to generalize gauge invariance to the non-abelian case, or we managed to generalize non-abelian global symmetry to the gauge case, whichever way you want to look at it. We managed to merge 2 important things about nature into one. And this is it. And there is such a thing for every possible Lie algebra. There are many Lie algebras. I can give you a list sometime if you're interested. And now L equals minus half trace f mu nu. F mu nu is gauge invariant. The last question to ask today is, well, what does this Lagrangian look like? Well, clearly it has a term minus half trace del mu a nu minus del mu a mu squared, and then it has other terms. This term is nothing but a generalization of the free Maxwell theory, and is the only quadratic term because these other terms come from interactions between that and this, or square of that. So schematically we can say the terms are of the form del a and a to the 4th. Del a comes by multiplying these terms with those terms, 1 derivative and 3 a's. and A fourth comes from squaring this term. For A terms, no derivative. Okay, but what do we call such terms in a Lagrangian in field theory? They are not part of the free theory. These are interaction terms. Okay, and moreover, because of this G, you can see that this comes with a G and this comes with a G squared. Okay, so the gauge principle has given us new interactions which are required. This is the first time. Earlier we saw that the symmetry principle, global symmetry, restricts what interactions we can have, but the non-abelian gauge principle says that, well, you can't have a free theory anymore at all. It doesn't make sense. In order to have the non-abelian symmetry, there must be a G, and there are interaction terms proportional to G and G squared. So the very existence of the symmetry implies the interactions. And the beautiful thing, and I'll ask you to go away and Google it now, this is a cubic coupling. In Feynman diagram language, it looks like this. So go to Google and type in 3 glue-on vertex. You can do it now if you like, and see what you get. There are experimental tests of this term and also of the last term. But very specifically, because these are unique signatures of this kind of theory. So the unique signature of this gauge principle, non-abelian gauge principle, is a 3 gluon and 4 gluon vertex. Now, what about photons? They don't have these vertices. So there is no Feynman diagram involving photon interacting with photon to give a photon. Okay, photons can only interact with E plus E minus or mu plus mu minus, or any charged particle plus and minus. But gluons can self-interact. So although we don't have any matter fields here, we don't have any phi's or psi's, any scalars or fermions, we still have an interacting theory by itself, unlike Maxwell theory, where only this much was there, and Maxwell theory was free unless we couple it to some other fields. Okay, so photon doesn't self-interact directly, and gluon or any particle described by Yang-Mills theory does. And well, it's a huge conceptual leap, because it means that instead of looking at these, so again it teaches us that if this is G, this must be G squared. You can't fiddle with the coefficient. If you put a 3 here or a pi or an I or anything wrong, you won't get gauge invariance. This coefficient must come exactly in step as dictated by minus Ig over here. Some references have plus Ig, that may come because of their choice of conventions. For example, if I shift A to minus A, then the sign of this term and this term, relative sign, will change. But there's no change which can put a factor here and not here. Well, now you'll say there is. I could scale A and I could put a factor here or here, but now this half would not be half anyway. If I scale A, this half won't be half. So once I normalize my kinetic term correctly, then the relative coefficient of those two is fixed, convention independent. Okay, I'll stop here, and I will see you next week Tuesday, but Sachin will see you tomorrow at 4 in that room.